Now, let us look into some of the examples related to jet transform, as per which jet transform of a signal x of n is given as x of z is equal to 1 by 1 minus 1 by 4 z inverse multiplied by 1 minus 1 by 2 z inverse with an ROC of 1 by 4 less than mod z less than half. We need to find the inverse jet transform of x of z, that is x of n. So x of z is not of any standard form. So by splitting x of z into partial fractions, that we can write that x of z is equal to a by 1 minus 1 by 4 z inverse plus b by 1 minus half z inverse. Upon simplifying this, we get that x of z is equal to a into 1 minus half z inverse plus b into 1 minus 1 by 4 z inverse divided by 1 minus 1 by 4 z inverse multiplied by 1 minus half z inverse. Upon equating the corresponding terms in the numerator, we see that a plus b should be equal to 1, which corresponds to the constant term. Other term is minus a by 2 minus b by 4 is equal to 0. That implies 2a plus b is equal to 0. So from this we see that b is equal to minus 2a. So a is equal to minus 1 and b is equal to 2. From this we can write that x of z is equal to minus 1 by 1 minus 1 by 4 z inverse plus 2 by 1 minus half z inverse. But the ROC is given as 1 by 4 less than mod z less than half. So the ROC could possibly be intersection of mod z greater than 1 by 4 and mod z less than half. So mod z greater than 1 by 4 corresponds to the first term and mod z less than half corresponds to the second term. From this, we can, by performing the inverse jet transform, we get x of n is equal to minus 1 by 4 whole power n u of n minus 2 into 1 by 2 whole power n u of minus n minus 1. This is the x of n required. Now let us look into another problem, as per which it's given that jet transform of the signal 2 power n into delta of n minus m is given as x of z and the corresponding ROC is R. We need to find the x of z and the ROC R. We see that the given signal x of n is equal to 2 power n multiplied by delta of n minus 1. Here delta of n minus 1 is an impulse at n is equal to m. From this we can see that x of z is equal to 2 power m multiplied by z power minus m. Also we see that the z transform x of z converges for every z except 0. So the ROC of x of z is every z except 0. Now let us look into another problem, as per which it is given that the z transform of a signal x1 of n is x1 of z and the corresponding ROC is R1, which is given as mod z greater than 1 by 3, and the z transform of x2 of n is equal to x2 of z with the corresponding ROC as R2. Now it is given that the z transform of a into x1 of n plus b into x2 of n doesn't exist. So from this we see that the intersection of the ROCs, sorry, the jet transform of AX1 n plus BX2 n doesn't exist, then we need to find the possible ROC R2. As the jet transform of the given linear combination of the signals doesn't exist, we see that the intersection of both the ROCs, that is R1 intersection R2, should be equal to pi. So from this we see that the ROC should be such that mod z less than b, where b is less than 1 by 3, because we see that for this case of ROC R2, R1 intersection R2 is pi. So the possible ROC R2 is mod z less than mod b, where mod b is less than 1 by 3. Now let us look into another problem, as per which the jet transform of a signal x of n is given as x of z, and the corresponding ROC is R. It's given that the signal is both non-causal and stable. Then we have to pick the possible ROC out of the options given. Option A is mod z greater than 2. Option B is 1 by 8 less than mod z less than 2. Option C is mod z less than 1 by 8. Option D is mod z greater than 1 by 8. We see that for the option A, ROC is mod z greater than 2, so the system is causal and unstable. So this is not the required ROC. As per option B, the system is non-causal and stable. So this is a required of ROC. However, we will check the option C and D as well. As per option C, ROC is mod z less than 1 by 8. As ROC is inside a circle, we see that the system is anti-causal and hence non-causal. Also, as ROC doesn't include unit circle, the system is unstable. As per option D, we see that ROC is mod z greater than 1 by 8. So as the ROC is outside a unit circle, we see that the system is causal, and also the ROC includes unit circle. So we see that the system is stable. So we see that option C and D also don't correspond to the required scenario. From this we see that 1 by 8 less than mod z less than 2 is the required ROC, as in this case the system is non-causal and stable. Now let us consider another problem, as per which the pole zero plot of the system function of the LTI system is as shown in the figure. There are two poles P1 and P2, and there is a 0 Z1. It's given that P2 is greater than P1 and P1 is less than 1. It's given that the system is non-causal and stable. Then we need to find the required condition that needs to be satisfied. From the given plot, we see that P1 is less than P2 and P1 is less than 1. So the possible ROCs of the system are mod z less than P1, P1 less than mod z less than P2, and mod z greater than P2. As the system is non-causal and stable, mod z greater than P2 is not a possible ROC, as in this case ROC is outside a circle. In case of the first ROC, the ROC is mod z less than P1, as P1 is less than 1, ROC is mod z less than 1. So ROC doesn't include a unit circle, so the system is unstable. So this is not a possible ROC as well. From this, we see that P1 less than mod z less than P2 is the possible ROC. As and also we know that in this case ROC is a ring, so the system is non-causal. Also, as the system is stable, ROC should include unit circle, so P1 should be less than 1 should less than P2. As mod z equal to 1 is the unit circle and it should be inside the ROC P1 less than mod z less than P2. So the required condition that needs to be satisfied from the given data is P1 less than 1 less than P2. Now let us consider another problem, as per which it is given that there is a signal x of n for which the z transform is given as x of z and the corresponding ROC is R. It's given that the ROC of the system function, the ROC of x of z is 1 by 3 less than mod z less than 2. Then we have to find the possible x of z from this out of the options given. Option A is 1 minus 2z inverse multiplied. Option A is 1 minus 1 by 3 z inverse multiplied by divided by 1 minus 2 z inverse. Option B is 1 divided by 1 minus 1 by 3 z inverse multiplied by 1 minus 2 z inverse. Option C is 1 divided by 1 minus 2 z inverse multiplied by 1 minus 3 z inverse. Option D is none of these are possible. From the given data, we see that in case of A, the possible ROCs are mod z greater than 2 and mod z less than 2, as ROC should be bounded by poles and it shouldn't contain any poles. So the option A is not correct option. As per option B, the possible ROCs are mod z greater than 2, 1 by 3 less than mod z less than 2, and mod z less than 1 by 3, because the ROC should be bounded by poles and it should contain any poles. So from this we see that 1 by 3, if the ROC is 1 by 3 less than mod z less than 2, option B is a possible x of z. However, if we check option C, the possible ROCs are mod z less than 2, 2 less than mod z less than 3, and mod z greater than 3. Here we see that 1 by 3 less than mod z less than 3 is not a possible ROC in this case. So option C is also not possible. So from this we see that out of the given systems, the system that could correspond to the ROC 1 by 3 less than mod z less than 2 is the system in the option B. Now let us consider, now let us look into another problem, as per which it is given that there is a signal which is given as x of n is equal to 1 by 3 whole power n u of minus n. We need to find the z transform of x of n. We know that if x1 of n is equal to 3 power n into u of n, then the z transform of x1 of n is equal to 1 divided by 1 minus 3z inverse with the ROC as mod z greater than 3. So from this we know that the z transform of x1 of minus n is equal to z transform of 3 power n, sorry, the z transform of 1 by 3 whole power n u of minus n is equal to x1 of 1 by z and the ROC is 1 by R, where R is the ROC mod z less mod z greater than 3. From this, we see that the Z transform of x of n, which is equal to x1 of minus n, can be written as 1 by 1 minus 3z, and the corresponding ROC is mod z less than 1 by 3. So, this is the required Z transform and the corresponding ROC. Now, let us look into another problem as per which there are two causal LTI systems with LCCDE, that is linear constant coefficient difference equation as given. The system 1 has the LCCDE as y of n is equal to half y of n minus 1 plus 3 into x of n minus 1, and the system 2 has LCCDE as y of n is equal to 1 by 3 into y of n minus 1 plus x of n. It's given that both the systems S1 and S2 are connected in cascade. We need to find the LCCDE that represents the cascaded system. From the given data, we see that the system S1 has got the system function as h1 of z is equal to 3z inverse divided by 1 minus half z inverse. This is by taking the z transform on both sides of LCCDE1. So the ROC of S1 is mod z greater than half. Similarly, the system S2 has the system function as h2 of z is equal to 1 divided by 1 minus 1 by 3 z inverse, with the ROC of mod z greater than 1 by 3. From this, we see that the overall system function h of z is equal to h1 of z multiplied by h2 of z. So the system function would become 3z inverse divided by 1 minus half z inverse multiplied by 1 minus 1 by 3 z inverse, and with the ROC as mod z greater than half, as the ROC is intersection of mod z greater than half and mod z greater than 1 by 3. But we know that the system function h of z is equal to y of z divided by x of z. From this, we can simplify the system function or the relation between y of z and x of z as y of z minus half z inverse y of z, sorry, y of z minus 5 by 6 z inverse y of z plus 1 by 6 z power minus 2 y of z is equal to 3 z inverse x of z. By taking inverse z transform on both sides, we get inverse z transform of y of z as y of n, and minus 5 by 6 times inverse z transform of z inverse y of z is y of n minus 1 plus 1 by 6 inverse z transform of z power minus 2 y of z is equal to y of n minus 2 is equal to 3 into x of n minus 1. So this can be simplified as y of n is equal to 5 by 6 y of n minus 1 minus 1 by 6 y of n minus 2 plus 3 times x of n minus 1. So this is the LCCDE that represents the cascaded system. Now let us look into another problem as per which there are four system functions given in the options A, B, C and D. In the option A, the system function is 1 minus half z inverse multiplied by 1 minus 3 by 4 z inverse. For the system B, the system in B, the system function is 1 minus 2 z inverse multiplied by 1 minus 5 z inverse. The system in C has the system function as 1 minus 1 by 4 Z inverse, and the system function in option D is 1 minus 1 by 3 Z inverse. We need to find for which of the above systems the stability implies non-causality. If we pick the system in system if we pick the system in option A, the possible ROCs are mod z greater than 3 by 4, 1 by 2 less than mod z less than 3 by 4, mod z less than half. In case of 1, the system is causal and stable. In case of the second ROC, the system is non-causal and unstable. And in case of third one, the system is anti-causal, non-causal and unstable. We see that from this there is no ROC which is both stable, which corresponds to stability and non-causality. So option A is not the correct one. In case of option B, the possible ROCs are mod z greater than 5, 2 less than, mod z less than 5, and mod z less than 2. We see that mod z greater than 5, in case of mod z greater than 5, the system is causal and unstable. In case of 2 less than mod z less than 5, the system is non-causal and unstable. In case of mod z less than 2, the system is stable, anti-causal and non-causal. From this we see that there is no ROC of system ROC that corresponds to stability and non-causality. So the system B is also not a correct option. In case of option C, the possible ROCs are mod z less than 1 by 4 and mod z greater than 1 by 4. Sorry, please note that in case of mod z less than 2, the system is stable and non-causal. So here the stability implies non-causality. So for the system in option B, with an ROC of mod z less than 2, stability implies non-causality. So this could be a correct answer. However, if we check the option C, in case of ROC mod z less than 1 by 4, the system is non-causal and unstable. In case of mod z greater than 1 by 4, the system is causal and stable. So the option C is also not correct one. In case of option D, the possible ROCs are mod z greater than 1 by 3 and mod z less than 1 by 3. So in case of the first ROC, we see that the system is causal and stable. In case of the second ROC, we see that the system is non-causal and unstable. So the option D is also not the correct one. From this, we see that option B is the system function. Option B corresponds to the system function, in which case the stability implies non-causality, as mod z less than 2 is the ROC, which gives that conclusion.